So far, we have been discussing about aqueous systems like systems in water. All reactions are done in water, and that ionization of a particular acid or a base in water. Now, let's study something like non-aqueous system. When did the concept of non-aqueous system come to existence? There are certain compounds which don't show their solubility in water, but they show their solubility in non-aqueous systems like you have glacial acetic acid, they have hydrogen halide, in fact liquid ammonia. So such systems are called as non-aqueous system. So commonly used reagents in organic synthesis, they are benzene, tetrahydrofuran, and then NN-dimethyl formamide. You also call this as NN-DMF. Mostly all compounds show solubility in these solvents. So these non-aqueous systems, they are very popular. Moreover, new non-aqueous systems like glacial acetic acid, hydrogen halides, they are also introduced in inorganic chemistry because many compounds do show their solubility in glacial acetic acid and hydrogen halide. So there should be certain criteria when we are selecting a non-aqueous system. The most important thing is the melting point. The melting point should be considerably low, and then boiling point as well. And then there should be some value for dipole moment. Dipole moment means existence as positive and negative pole, as a result of which ionization of a particular acid or a base. Let's say a simple example of an acid which is HX. So this dissociates or ionizes giving H plus and X minus. So now if you have a solvent that has dipole moment, then these positive ions will be surrounded by negative end of the dipole, and the negative ion will be surrounded by the positive end of the dipole, as a result of which they won't be interacting with each other and then forming HX molecule. So ionization will be practically possible. So we have to look into different factors such as melting point, boiling point, solubility of a particular compound, as well as the dipole moment when we are deciding the use of non-aqueous systems, or whether we should go for non-aqueous systems in preference of aqueous system. Then let's move on to the next part, which is Lux flood concept. Lux flood concept is not generally used, but it provides a very good idea about systems in which there are no protons. So according to Lux flood concept, base is an oxide donor, whereas acid is an oxide ion acceptor. Now let's take a very simple example. You have calcium oxide, which contains metallic calcium. So oxides of metal are basic in nature. Now if I have to write calcium hydroxide plus silicic acid, I could form calcium silicate plus water. But what if I really don't want to use the proton or OH? So in this case, calcium oxide will react with SiO2 to form CaSiO3, which is calcium silicate. So this explains the basic nature of calcium oxide and acidic nature of silica without even taking into account the H plus and OH minus ion. So this is very important generalization of the Lowry-Bronsted concept, in which was put forward by Lux and Flood, and it says base is an oxide ion donor, whereas acid is an oxide ion acceptor. The common example for this reaction is calcium oxide reacting with silica to form calcium silicate. This is nothing but a white infusible mass, most of the time white if it is not contaminated with other impurities.